Okay, I think this is on. I am going to give you guys a video on parallelograms and the theorems and a few examples. So let me give you a screen share and we'll go over a couple things. So this is lesson 28 is what this is, and we'll start here. Well, let me get that back. We'll start here. So this is our learning target. We want to develop and prove some properties of parallelograms. And a parallelogram is a quadrilateral, so it has four sides. Let me get my pens up while I'm talking. And this, now I got my pens up. Okay, so a parallelogram is a quadrilateral with both pairs of opposite sides being parallel. And then this particular symbol right here, a little kind of like a small version of a parallelogram, can be used just like you would if you were saying, like triangle ABC. This one here, we would write it this way down here where I'm boxing it off. Parallelogram KATY would be written like that. The thing about it being opposite sides being parallel would be shown in the diagram here. If you look at the line going through A and K, that line is parallel to the line going through Y and T, and then the line going through Y and K is parallel to the line going through A and T. So those are parallel lines, and you can see they're marked that way in the diagram. Okay, consecutive angles. If we're starting out with angle K, so for instance, in this little question here, to help us identify consecutive angles, they will want to know which angles are consecutive to angle K. So right here's angle K in the diagram. If you go clockwise, the next consecutive angle to K would be angle A over here. And if you go counterclockwise, the next consecutive angle to K would be angle Y right there. So that's listed here in the notes. All right, then there's some theorems that we have available to us, and we will end up proving, we prove most of these when we go on and do the next thing here. So the first is that consecutive angles are supplementary. So this right here is our first theorem. So if they're supplementary, that means they add to be 180 degrees. So when we look at this diagram, we'll go back up to the KATY parallelogram. I will show you how you can see that those must be supplementary. If you extend these lines that are parallel and then extend this line here, we get ourselves a transversal. I clean that up a tiny bit. So we get that transversal. And when we look at the transversal, what we can see is you can label like that could be angle 1, this up here could be angle 2, and properties of transversals lets you say that corresponding angles are congruent. So up here would be another angle 1, like it is where it crosses that parallel line below. And so now it should be easy to see that if you add angle 1 plus angle 2, you would get 180 degrees. And so anytime you add angles 1 and 2, you're going to get 180 degrees. Well, that works inside as well. So when we add this angle 1 with this angle 2, they will have to add to 180. That's supplementary. So those are consecutive angles going from K counterclockwise. Let's refigure and look at going clockwise from K over to A. So we clear this. So if we do parallel lines in the other set, where these are the parallel lines we're dealing with, and then the transversal coming through here, we can make the same argument where this could be 2 and this could be 1, and things in corresponding positions would equal, and so this angle over here would also be 1, and then you can see the same argument we just saw, just in a different orientation, where that must equal 180 degrees. And so when you add angle 2 and angle 1, that's what you're going to get. Well, you also have angle 2 and angle 1 as interior angles right there. And so angle K added to angle A, those must be supplementary. And so that supports, and in fact, that proves that theorem. So we can clear that. The next thing that we have going on is each diagonal of a parallelogram divides that parallelogram into two congruent triangles. We will prove that in a minute, but right now, this triangle and this other triangle, those would be said to be congruent, but we would need to go prove that. We will. It is true, and so that is a property we can keep. It's a theorem, but we'll prove it. The next theorem for us is that opposite sides of a parallelogram are congruent. So in this one down here that I'm working with, DIAG, we're claiming that's a parallelogram. So the segment GD and the segment AI are congruent, and the other congruent sides are DI and GA. Those would be congruent. So you get congruent sides on opposite sides of a parallelogram. And the next one, of course, if I'm going too fast, you can always pause, rewind. The next one here is that opposite angles of a parallelogram are congruent. Rather than show you in this one that I was just working in, that already has that diagonal drawn in. Let's go look at it up here in the quadrilateral, the parallelogram, KATY. What this is saying is opposite angles are congruent. So angle Y and angle A would be congruent, and angle K and angle T would be congruent. So that's something that we also will prove when we go on to the next thing we're going to do. All right, and then the diagonals of a parallelogram bisect each other. So down here in DIAG, there is one diagonal drawn in. If we drew in the other diagonal from D to A, what that does, and I spilled over a bit, let me do this once more. What that does is they bisect each other. So I'll use a different color. These two well, that's a tougher color to see. Let's just stay in white. These two segments would be the same, like label that point of intersection, maybe X, that's the point where they cross. And then the segment from X to I would be congruent to the segment from X to G. And the same thing would be true on the other diagonal. These are congruent. So D to X is congruent to A to X. So that is something, again, that is without proof at the moment, but that is provable. So that theorem we will take advantage of. And then the last thing, this is not actually out of the text that you have, but it is a true statement. Interior angles add to 360 on a parallelogram. In fact, that's true for all quadrilaterals as long as they are convex quadrilaterals. So if you have something that isn't convex, something like this with four sides, that won't have 360 degrees guarantee on the internal angles. This angle, you'd have this massive wide angle, and then that angle and that angle. That doesn't get you 360. But if it is convex, like our parallelograms are, I'll do a parallelogram. These pieces, angle, 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 add that all up. It's sum. I'm trying to write sum. My pen is floating in space out here. Okay, the sum is 360 degrees. And if we need to say, well, how could it be? Take a look at this. If you split it into two triangles like this, the triangle in green on this side, we know that would have 180 degrees of angle for all of its angles that I just marked in green. And then the triangle on the other side that I'm marking in red, it would also have angles here, here, and here that add up to 180. And if you combine all those angles, it's the same as the white parallelograms angles behind it, and 180 plus 180, you guessed it, it's 360. So that's true of not only parallelograms, but all convex quadrilaterals if you need that. Okay, so that gets us through all these properties. Again, you can back it up and look at it closer. I am going to go now and show you some examples and prove some of the things we just talked about. Is what I said I'd put in the video. So here we go. All right, I will say goodbye. I'm going to try to get my camera off. All right, technical difficulties. Apologize. This will just take a second. This is either technical difficulties or user error. Maybe it's user error. Here we go. Okay, now back to the screen share and tablet mode. Okay, here's what we shall do. We're going to prove, let me get some stuff to write. We're going to prove opposite sides of a parallelogram are congruent. Okay, prove opposite sides of a parallelogram are congruent. And what we are going to be given is we will be given a parallelogram. That's a little too big. Parallelogram DIAG. And I'll draw this in. Trying to make that look like a parallelogram. All right, and so label this around the outside, DIAG. Eventually, it's going to help us to have a diagonal in there. I'll draw that in a moment. In the notes that you can see in Classroom, I have kind of a paragraph proof, which takes up the first half of the notes, and then I put it into a 2-column format. I'm going to just do the 2-column format here. It looks like, oh, there's all this writing. If you look at the slides, just focus on the 2-column format, and that's all the same information. And so there's it's much more concise. So here it goes. We have statement, and we have reason. And to start with, we need to talk about what do we actually know when we're given a parallelogram. And so the given, of course, is the first thing. So we have, I gotta write the right symbol. We have parallelogram. It looks more like a rectangle. Let me be picky about it for a second. Okay, there we have parallelogram DIAG, and by stating it that way, that's our given. Now, what we know about parallelograms, all those other theorems we said are going to need to be proven, but the one thing we know from the definition of a parallelogram is opposite sides are parallel. So we can now say that DI is parallel to GA and DG is parallel to IA. And these are segments. I think in my notes, I didn't mark them as segments. Okay, so that's top is parallel to bottom and left side is parallel to right side. That's what we're claiming right now. And that is from the definition of parallelograms. So definition of parallelograms supports that idea. Now, what we're going to do is we're going to split this thing into a triangle. So I'm going to draw in this diagonal, the IG diagonal. And we're going to talk about the angle that is DIG. We're going to talk about this angle right here, DIG. So angle DIG, we're going to claim that's congruent. We said these should make congruent triangles. We're going to say that one is congruent to angle AGI. We're not just going to say that, we need to be able to show it. So A to G to I gets us this one down here. And so the way we can get there is by doing a transversal. So take a look at what we can see here. If you extend that line that's parallel to that line and run this transversal through it, now what you have is alternate interior angles of your transversal. Those are known from earlier work to be congruent. So this is going to be, the reason we're going to use here is alternate interior angles. All right, so I'm going to come back and erase this. I don't want to clear, I just want to erase, take this stuff away. But at the moment, if I want to leave my markings out here in blue, what we have right now is we do have this and this are the same. Now what we do is, just like I was showing you for the consecutive angles being supplementary, we do our transversal, just imagine it in the other plane. And so now run this, let me do that better. Run this line as one of the lines that's parallel and that is the other. And we can again run this diagonal through as the transversal. And what we've got now is we have this, I'll do in a new, well, I'll do in red, this is my color. This angle is alternate interior to this angle up here on the transversal. And so maybe I should do that in 2 marks because it'll separate it from the one we already marked. So those 2 angles are congruent, but I haven't claimed that in my theorem here, so, or in my 2-column proof. So let me come down and claim that. It's angle DGI is congruent to angle, we went DGI, so we should go AIG for the other one, angle AIG. And this is again by alternate interior angles. Okay, I'm going to take out what we've been writing just to get it all cleaned up and look like it isn't all scattered and busied up again. And so what we just got was, I didn't mean to erase that. Let me put these pieces back. Okay, what we just got was this angle and this angle are congruent. And we defended why. So from here, we're trying to get these 2 triangles to be congruent triangles, because if we can get congruent triangles, then we can claim corresponding parts of triangles, and that'll get us the opposite sides being congruent, which was what we're after. If you go back up and look back at what we were trying to prove, opposite sides of the parallelogram are congruent. If these are congruent triangles, we'll have that. So when we look at what we would need to get to congruent triangles, what we have is we have an angle, and then we have another angle. If we could get the side that they share that's between them, we would have angle, side, angle on the triangle in yellow. And so we want to get that same thing going with the triangle that I'll do in black. And so if we had angle and then the side that goes between them and another angle, and we could say angle, side, angle, and they match. So that would get us congruent triangles. All we need is this reflexive that they share that side, IG. So that's what we need. We have that IG segment is congruent to, I'll change it to GI segment because it actually does go in the other order around the other triangle, but it's it could be left the same. And this is reflexive. So we just proved one of our theorems we were saying we need, we were going to come in and prove, but it's not the one we're after quite yet, but we're most of the way there. So if we come back in here and erase the parts that I added, I may not be able to erase them without erasing more than I want. Yeah. But I can put this back. Okay, so because we used that reflexive and said that segment there is reflexive to itself, we can now claim that triangle DGI is congruent to triangle AIG. Those are the two triangles, and that's going through angle, side, angle. From there, we can get that opposite sides of the parallelogram are congruent, because once we have these congruent triangles, what we are able to say at this point is, let me get a color here. We can say, hey, this side here in orange coming out of the angle marked with 2 is the same as this side here next to the out of the other triangles, the black 2 angle marks coming out of I. So those segments are now congruent from corresponding parts of congruent triangles. And the other piece that we can see is, for the same reasons, this side up here that I'm doing in pink comes off the single marked angle, and this side here is also the corresponding part of that lower triangle coming off that single marked angle. So I get both of those by having congruent triangles. So we get that DG is congruent to its opposite side. I'm doing the part in orange right now. DG is congruent to AI. And we get now the pink part, that the segment DI, the top segment, is congruent to the segment AG, the bottom pink segment. And all of this comes from corresponding parts of congruent triangles are congruent. Okay, so we proved what we were after up here, that the opposite sides of a parallelogram are congruent. Now, if we wanted to get opposite angles are congruent, it wouldn't take very much more. I'm not going to make a formal proof out of it, but just think through this with me. There's only a little bit more that's needed. Basically, if you try and do this angle, well, let me do the easier one first. These angles already are the same based on, well, that's not pretty. Based on corresponding parts of congruent triangles, you get angle D and angle A to be the same. So we have that opposite pair. And then on the other side, again, this isn't going to be formal proof, but just notice this. If you did, let me get the right color. If you add angle 2 plus angle 1 together right here, that's the same as adding angle 2 and angle 1 together over here. And that would be the same sum coming out of these corresponding, or coming out of these congruent triangles. This angle plus this angle would be the same total sum, whether you did it in the left corner or that angle and that angle making the same sum, or if it were up in the right top corner. And that's your other pair of congruent sides. So that wouldn't take much more to get yourself to that other theorem that we said we had. All right. You can slow down and look at that again if needed. I'm going to move to doing just an example or two so you have those to look at if you want them. So this is available in the notes. I'm going to clear it. And here's the last thing we'll do. We'll do some quick examples and see how this is used. So if you're given parallelogram LUCK, so I'll make my parallelogram we'll label it LUCK. First, let's just match some things up. This would be like a fill in the blank type of thing. If you have triangle KCL, what is that congruent to? And so when we see KCL, let's fill in the piece that's missing. So they are not showing us the extra line. So from K to C to L, would need that diagonal drawn in. And so the order matters, right? We start at K and we go to C and then we go to L. And so we need to match it up. It may not be obvious because this thing is so much like a tilted square, like a diamond, where the side lengths are the same, which is a rhombus. So if we needed to help ourselves really see the ways this works, make an exaggerated example for yourself and then connect that. Oh, I'll do the other diagonal because they do the other diagonal. That doesn't look good. If you look at this and you went, I'll do a different color. You went from this corner to here to here, you're going down the long side and then up the shared side. So if you went to the other one that's here, you'd have to start and go down the long side. I'm going the wrong direction. Sorry, I'm looking at that like, wait a second. I'd start over here. I'd go down the long side and then up the shared side. So in our diagram, we need to do the side up there and then up that way. So this will be ULC will be the thing that it's congruent to. And that would make this black one. Okay, so we've got kind of that fill in the blank style question of just, hey, orientation matters, and these exaggerated, like longer than they are tall ones can help us see it easier. Then a second type of thing we would need to do is, what if we have some unknowns in the side lengths, things like that. So I'm going to clean up some of these things I've written in on here. Okay. So what if, let's do this. Let's solve for x if the measure of angle KCU is 10x minus 15. And we also have the measure of angle K equal to 6x plus 3. So they give us KCU. So the angle for KCU, I'll put this in a color. I'll do this in red. So KCU right here is 10x minus 15. And then angle K, they assume, we still maybe have that diagonal drawn in. But it's not there anymore. So that's why they do KCU and just K for the other one. This one is 6x plus 3. Now, this takes us back to what we showed on the very first page when we were looking at all the theorems. Consecutive angles are supplementary. So what we are able to set up is that 6x plus 3 plus 10x minus 15 must add up to 180. So do some algebra, 16x, negative 12. So we're simplifying that right side. Now add 12 to both sides. You got 192. Now divide both sides by 16, and what you get out of this is 12. So we were trying to solve for x, and so here's our x. It's 12. And we used the fact that consecutive angles are supplementary in order to do that. Okay, another type that we'll do is we'll do one more in this one. We'll do a part C. And this would be where we want to solve for x again. But this time they're telling us KL segment, the segment length is 2x plus y. And then they're telling us that LU is 7. UC is 14. And finally, KC is 5y minus 4x. Need an equal sign in there. So this is what we're given. So come back up to our drawing up here. I'll take away the information we had from the last one. And let's put in these side lengths. So KL is 2x plus y. LU is equal to 7. UC is equal to 14. And KC is 5y minus 4x. Now in this, we have the property that opposite sides are congruent. So those two pieces should match that I circled in green. So we should be able to put that down. We should be able to say one equation we know is true is that 2x plus y equals 14. Now, a second thing that we should know is true is, this would be a second equation that we would have, is we should know that 7 is equal to 5y minus 4x, because those are also opposite sides. So if we have 5y, I'll put it over on the right. I'm going to move where I'm writing this. So equation 2 would be that 5y minus 4x equals 7. Okay, well, this becomes something that we have x and y in both equations. This is a system of equations. We have to use a system to solve this. I'm going to use substitution. So to do substitution, I'm going to solve one equation for one of its unknowns. I'm going to solve equation 1 for the y variable. So I'm going to minus 2x on both sides, and this will bring us to y equals negative 2x plus 14. I've isolated y, and so now I'm going to take that value that I isolated and I'm going to plug it in for y in the other equation. It's going to go right here for the y variable. So I'm doing the substitution step. So as I start writing this next one down, I'm plugging in, I've got a split like that. I've got 5, and where that y is, I'm replacing it with negative 2x plus 14. Now I can finish, I've finished subbing in the y, so I finish up the rest of the line, minus 4x equals 7. Do distributive property here, minus 10x plus 70. That's 5 times 14. And so now combine x's, we would have negative 14x plus 70 equals 7. Subtract the 70 off. So I'm not going to write the step, but I'm telling you it. And so that gets you a minus 63. And then divide by negative 4. When you divide by negative 4, 63 doesn't come out a whole number. It comes out 4.5. Negative divided by negative is a positive. Okay, now that we have that, we can say, oh, well, now that I know what x is, I still want to know y. You come back up and plug x into this equation. You could have gone back to the originals, but this is the easiest place to put it. So now we have y equals negative 2. Plug that x in. That's 4.5 plus 14. So y equals negative 9 plus 14. Y equals, that would be y equals 5. So now you have both values. You have the x and the y. You could even write them as a xy pair if you wanted to. It's 4.5 comma 5 would be our solution. Okay, so there's some application of it. Yeah, so the questions you have are downstream from this, and hopefully this will be helpful for you to see where these properties come from and a little bit of how you use them. All right, I will get back to the main screen and I'm going to stop my recording. I'll see you later. Bye.